Okay, so last day, we did a really long lesson on a periodic table. I'm just gonna like flash through my slides and go over a couple of like the concepts that we learned, and hopefully you'll recall a couple of these. How is the periodic table ordered? By number. They are literally in numerical order. It goes 1, 2, 3, 4, 5. The periodic table would be really stupid if number 1 was right here, 2 was right there, 3 was right here, 4. Like that would be the dumbest way of doing things. Right? So it goes by number 1, 2, 3, 4. One of the things that we got to at the end of the day is, what does that atomic number tell you? It tells you how many protons something has. If I didn't get a chance to fully make that connection, now I want to make that. If hydrogen is number 1, it has 1 proton. If helium is number 2, it has 2 protons. If copper is number 29, it has 29 protons. Does that make sense? And that is what defines its name. Okay. Now, one of the things that we started working on last day, but again, we were kind of running out of time, is a notation that looked like this. I might give you an unknown element, and in the bottom corner here, I might put a number. I'll tell you the element today. Let's go with carbon. I guarantee you carbon has a 6 in the corner. It has to. Guaranteed. If I'm putting the symbol here, C for carbon, it better be in a 6 in the corner, because carbon is number 6, which means it has 6 protons. Does that make sense? This is physically impossible. It cannot be H6. It cannot be N6. It cannot be I6. Okay? Then the letter that we go with, the name we have, and the number of protons has to match up. So hydrogen has 1, nitrogen has 7, and iodide is number like 35 or something like that. I don't actually know which one iodide is. Here, I can look at yours. 53. Does that make sense? That's called the atomic number. Okay. Next thing we talked about, there's a bunch of different categories on our table. Okay. You need to know natural versus synthetic. Cliff Notes version on this, because I don't want to reteach all of yesterday. I just want to like recap. If I give you an unknown compound, and in this corner up here there's a number, and that number is in a bracket, it's synthetic. Okay. And if it's like got some decimal numbers to it, it's naturally occurring. I don't know that I can explain to you yet why there's the difference, but if you can just accept that that is how we're going to tell the difference, go with that for now. And later, as I teach you more and you learn this better, then I can explain why we're doing that. And the analogy I want to give is I'm teaching Cami how to read. Right? I don't teach her all the crazy little weird things like silent letters and how pH says F, right? Like, we start off with the basics. That's okay. If you really need to know why, I'll explain it to you. Okay, but like it's going to take a while. Okay. Other things we talked about, metals versus non-metals versus metalloids. I'm going to go to this slide right here because this one's got a good picture. In blue, you've got your metals. They're all on this side of the table. I don't know whether I mentioned this, though. Hydrogen is an exception. Maybe I didn't say that yesterday. Hydrogen is on this side of the table, but it's actually considered an exception. Some periodic tables actually put hydrogen over here. And they actually start with 1 and 2 over there before going back to 3 and 4. So, yeah, I didn't say that yesterday, did I? Hydrogen is actually not considered a metal, which makes sense because what state of matter is hydrogen? It's a gas, yeah. Okay. So other than that, all these blue ones over here are metals. The ones along the staircase are metalloids. And then these ones here, plus hydrogen, they're the non-metals. And we define them based on properties. So metals are strong and ductile and conduct electricity. Non-metals don't. Like, I didn't even put a lot in my notes here. I just said they lack the properties of metals. So like they're the exact opposite. Metalloids, they do like half of each. Someone yesterday, give me one sec here, just remind me. Someone yesterday asked whether mercury was a metalloid because they knew that mercury was kind of like a liquidy kind of metal. And that was a great question. That's not how we define them. Mercury is still considered a metal. It just happens to be liquidy because it melts really low. That's all. If we wanted mercury to be a solid, just make it colder out and it would freeze. Does that make sense? What really defines them as metalloids is that like a metalloid might be strong and it might be hard, but it is not malleable and it is not ductile. Does that make sense? So like of all the properties on the list, a metalloid would have like half of each. Yeah. Oh, I'm so sorry. Yes, absolutely. Sorry, you should have stopped me there. I didn't realize that wasn't a question. Yes. Are you going to be okay? Like, do we need to call for help? do what you need to take care of yourself. Sorry, I didn't realize that was your question. Yeah, just go. Popped his shoulder out. Yikes. Okay, everybody, that was kind of a distraction there. Everybody kind of okay on those initial properties there? Okay. Then we talked about things called groups or families. Okay. Groups go up and down. And when Mendeleev made his periodic table, up and down meant these things have similar properties. For right now, because we're still kind of starting out, the property I wanted you guys to notice was charges. Everybody in this group looks like he's +1. Everybody in this group was +2. Everybody here is +3. Like there was a lot of similarities there. Okay. Some of them even have special names. Families or periods, families or groups. Families go up and down. Periods or rows, they go side to side. And the note that I made in these is that these are about how many like energy levels they have. And energy levels is usually where some kids I start to lose them. Because as soon as I start drawing diagrams with like rings going around things, that's where kids start to go, whoa, hang on, what just happened here? So I want to pause for a second on those. Let's pick a random element. I'm just going to go with, let's say, carbon. Carbon is number 6. That is what defines it as carbon. It has to be number 6, which means in its nucleus there are 1, 2, 3, 4, 5, 6 protons. That's where the protons are found. And in these like energy, like, I don't know, rings, that's where the electrons are. So I'm going to draw a whole bunch of energy rings. Now, there's a bit of a pattern to this. In the first ring, it is full when it's out of 2. That's as much as capacity as it can have. That's what we've discovered. Which explains why on our periodic table, the first row has 1, 2 in it. As soon as that was full, we start our next row. And our next row is full after 1, 2, 3, 4, 5, 6, 7, 8 more. So the second row has a capacity of 8. Fill that row up, you got to go to the third one. It also has a capacity of 8. Go past that, it's 18. And we can talk about the math behind those ones later, but this gets us started. Now, another thing we talked about yesterday is that protons equals electrons. So if carbon has 6 protons, it also has 6 electrons. So the question now is, where do those electrons go? So to me, like, I think of an analogy of like maybe a hotel. The first floor of the hotel fills up after 2 rooms are out. The second floor has 8 rooms, the third floor has 8 rooms. And we need 6 protons and 6 electrons. So where do they go? Well, the first ring has 1, 2 electrons in it. It's now full. So move on to floor 2. Floor 2 has the ability to have 8, but like if we've just filled up 2 out of 2 and we need to get to 6, we only need 4 out of 8. Does that make sense? Because these 2 plus these 4 will give us the 6 we need. So this ring has 1, 2, 3, 4. And there's more room on that floor. That's just how full it happens to be. Okay. Those are known as your energy levels. And if I go back to periods, there are 7 of them. There are 1, 2, 3, 4, 5, 6, 7. And we talked a bit yesterday about how these are not new rows. They just kind of slot in right there. Yes? Yep. Good question. That's actually going to lead into something we're going to talk about. The word we're going to use is called stable. Someone yesterday even asked me, how do we create stable ions? So stability basically means that we want electrons, to the best of our ability, to have a full level. Okay? Electrons don't seem to like to be like half full or like over full, if that makes sense. And so if it was exactly full, those electrons probably wouldn't jump. Okay? But if they weren't full and there was like, yeah, it's possible that those ones could jump from one level to the other actually. So I guess to answer your questions, yeah, it's possible that all of a sudden you could have an extra one. But they don't overfill a level. What they would do is like the electron from here would jump up to the next one, to one that's empty. So let me just rephrase my answer again then. The electrons don't want to overfill a level, but like this one right here, this electron could possibly jump way out to like that ring. If that makes sense. That's actually what you see when fireworks, actually. When fireworks blow up and explode and you see all those colors, what you're actually seeing is the electron jumping from one level to the next, and it actually releases color. Does that answer your question? Cool. How's your shoulder? You okay? Okay. Okay, we talked a bit about atoms, and this is about where I started to maybe lose some of you, because I know I'd been talking for a long time. I'm sorry, it's just a long lesson. Okay, and this is that same sort of picture here. Why don't we look at this atom right here, and let's see that we can figure out what it is. I don't imagine any of you are good enough to be able to look at that nucleus and see how many protons are in there. But you could count electrons. Let's count the electrons. There's 2 in the first level, so 2 out of 2. Second energy level, there's 1, 2, 3, 4, 5, 6, 7, 8. Third energy level, there is 1, 2, 3, 4, 5, 6, 7, 8. Fourth energy level, there are just 2. We should be able to figure out who this is. This would be number 20, yeah, right? So if this is number 20 for electrons, it better be number 20 for protons, which means I now know who it is. This is calcium 20. Is that starting to like fit together a little bit there? So if you don't know who somebody is based on protons, you could use electrons. And that's what we kind of have in this picture here. It's more of what I've been talking about. What I need to get to now is neutrons. And I just started doing neutrons at the end of last day, and then I was running out of time. So let me get to a slide like this one here. So this is about where we left off. I guarantee that the bottom number here is 6. I guarantee it if you put a carbon here. It has to. Those two things match up. It is not allowed for carbon to have 7 protons. Because if carbon has 7 protons, we don't call it carbon. We call it nitrogen. I have a really dumb analogy for this. This is stupid, but go with it. You guys ever watch this show, The Smurfs? My daughters love The Smurfs. The Smurfs base their identity all around one characteristic. Like Grumpy Smurf is grumpy, and like Clumsy Smurf is clumsy, right? Like we call them what we call them based on like that identity. I want to use that analogy to talk about this. Why do we call nitrogen nitrogen? Because nitrogen's identity is tied up in the 7 protons it has. If nitrogen somehow had an extra one, and it was no longer nitrogen with 7, it was nitrogen with 8, we wouldn't be able to call him that anymore. And if Grumpy Smurf decided to start being happy, we couldn't call him Grumpy Smurf, we'd have to call him Happy Smurf. Does that make sense? So the name would change to something new depending on that number. But here's what's different though. Neutrons are neutral, and you can have any number of neutrons you want. You could have 1 or 4 or 300 neutrons, and that doesn't change who you are. And that's the top number we put up here. When there's a number up top here, that's called a mass number, and it's how heavy something is in terms of protons plus neutrons. So if you want to figure out how many neutrons something has, you just subtract the 2 numbers. If I have 12 and 6 here, there are 6 neutrons. But if I have 14 and 6 here, there are 8 neutrons. The idea being that I guarantee you there's 6 protons. Either way, carbon is carbon because of its 6 protons. This guy's just heavier. It's got a little bit more fat to it, I guess, if that analogy works, right? It's just heavier. Let's say I put on an extra 30 pounds. I eat a lot of food over Christmas vacation. Am I still Chris, though? Yeah, I'm just a little heavier, that's all, right? Or if I lose some weight and I go from being 14 down to 12, I still call myself the same name, because your identity is the bottom number. You had a question. They are, yeah. So neutrons and protons are in the nucleus, which is why they're part of this number up here, and electrons are not. They're the ones that are in those orbiting things. Alexa. Good question. So this is a good question here. Let me give you the best answer I can based on what I think you guys know so far. Have you guys heard of things called radioactive things before, where like they give off radiation? Okay. If a nucleus has too many neutrons, it can become unstable. And what ends up happening is the nucleus will actually break apart into pieces, and in doing so, it gives off radiation. The sun is a classic example of something that like gives off radiation. Only it gives off light, which is good for us. Does that make sense? So there's a general rule of thumb that you can probably have about twice as many neutrons as protons. And if you ever start to get above that line, then radioactive decay starts to happen, and it actually will like literally break apart and become radioactive. Which explains why on your periodic table, most of the ones that are radioactive are at the bottom of the table, because they're very, very big. The bigger the nucleus gets, the more unstable it is. Does that make sense? So I think a little while ago I said you could have 1 neutron, 3 neutrons, or 300. I kind of was exaggerating the 300. If you had 300 neutrons, it would probably break apart. It couldn't handle that much. But neutrons are arbitrary. You could have 3 or 4 or 5 or 6. It really doesn't matter. So I want to try some more practice examples, and I think this is about where I left off. So let's try a couple more practice examples. Find somewhere you can write these down here. And I'm going to do 2 different activities or games, kind of. The first one I'm going to do is I'm going to give you an unknown element. I'm going to call it smiley face. This is a newly discovered element called smiley face. And I'm going to give you a couple of numbers. I'm going to tell you that it's 19, and let's go with 9. I want you to tell me who it is and what it's got inside of it. Don't yell the answer out. Second game I'm going to do. I'm going to tell you that we have, let's say, 4 protons and 5 neutrons. Tell me who this is. Okay. So 2 different ways of writing this. Can I give you guys like 1 or 2 minutes to try this? And then let's talk about it. Just don't yell it out. Don't spoil the game for everybody else. So my question in the first one is, who is smiley face element? What is his name? Is this Grumpy Smurf or Happy Smurf or Clumsy Smurf? What would we call him? It would be fluorine. F for fluorine. Why would it be F for fluorine? Because the bottom number is 9. Did some of you guys say it was potassium? You were looking at the top number then. The bottom number is defines whose you are. So this bottom number means you're number 9. And number 9 on the table is fluorine, right? So it's no longer unknown smiley face. This is fluorine. How do you spell it? U-R-R-I-N. Okay, based on the bottom number. Okay, let me keep going here though. So the bottom number defines it as fluorine with 9 protons. If I asked you how many neutrons it had then, the answer would be 10. And that's where the 19 comes in. In this nucleus, there must be 19 particles in the nucleus. 9 of them are protons. That's what makes it fluorine. That's why we call it fluorine. Well, 9 plus what makes 19? 9 plus 10 makes 14. So it's 9 and 10. Let's try the other one here. This has been written upside down, okay? 4 and 5. I really could have written this exact same thing with, let's make this one frowny face, I guess. And the numbers that I would have to use here would be 4 in the bottom. What would the top number up here be? 9. Because 4 and 5 adds up to 9. The question then is, who is this? What do we call this particular unhappy Smurf? Beryllium. And I know it's beryllium because beryllium is number 4. Okay. So we care about the bottom number, which is protons, when we ask you, what do we call you? Okay. I'm going to move on, but I need you guys to know this, okay? I believe in my learning cycle concept. This is the knowledge stage here, okay? If you're still not fully getting it, don't quit. Don't give up on me and go, I don't get it, I quit, okay? We'll practice, right? We got to try it. Okay? I'll give you more examples. I'll give you more things to work on. It will sink in. Here's what I didn't get to last day. The last thing we have to do is talk about something called ions. Okay. And someone yesterday asked me about like how ions become stable, because maybe you've heard of ions before. Ions are, where do I have this here? Well, I'm going to get to ions in a second here. Maybe I'll talk about this slide here for a bit. Can you guys find this picture slide right here? A couple of you have it. What you may notice on this diagram here is that there's a lot of similarities. Let's take a look at everybody in the first column right here. Everybody in the first column was a +1. I want to now explain why they were all +1. I wasn't ready to yesterday. I think I can explain it now. Why is everybody here +1? I want you to look at their last electron ring. You see how this guy has 1 electron in his last ring? And this guy in his outermost ring has 1 electron. And this guy in his outermost ring has 1 electron. Hey, did you guys notice that everyone there was +1? Let's keep thinking here. This one in the outermost ring is +2 because there's 2 electrons in the outermost ring. And this one also has 2 electrons in its outermost ring. There's a bit of a pattern to this that leads to it forming ions. And ions have like a plus charge to it or a minus charge. And the word I want to use is called a valence electron. That's the slide I'm kind of skipping here. A valence electrons are defined as the electrons in the outermost level. So like draw all of your electrons in those like rings, and all you've got to do is figure out how many are in the last ring. And that tells us how it's going to form an ion. I want to go back to my picture here. Stability in compounds usually occurs because it's either got a full energy level or an empty energy level. Okay. I want to talk about this one right here. This energy level, let's do lithium, Li. Lithium has 3 electrons because it's number 3. So there's 2 in the first level, and then the next level there's 1. So it would have been 2 out of 2 for level 1 and 1 out of 8. If your progress towards something, I don't even know what you're working towards, but let's say that you finished level 1 in a video game. You finished 2 out of 2 tasks. You're moving on, right? And you're at the next level of the video game, and you're at 1 out of 8. Have you really finished all that much? No. And you know what? Electrons work the same way, is that like, they're not really close to being finished. And what it would rather do, it would rather either be like entirely full or entirely empty. So if I can use the video game analogy, imagine that you can only save the video game at the end of every level. And your mom calls you down for supper, and you're at task 1 out of 8. Should you keep playing and try to get all the way up to 8 out of 8? Maybe you'd like to. Or did you really not get all that far? Should you just quit and you have to start over at the beginning? You get what I'm saying here? And so here's what happens in ions. Lithium says, I've got 1 electron out of 8. It then tries to get rid of that electron. And it basically says, I can't fill this thing up, so let's just get rid of the 1 that's like a little bit extra. Well, now here's what happens. Remember how lithium, the 3 in the bottom, defines it as lithium because of it having 3 protons? But now how many electrons are there? There's only 2 electrons left. Well, now do your protons and electrons, do they equal each other? No. What is there more of? Protons. How many more protons are there? 1. Which is why everything in this column is a +1 charge. Let me try a couple more of these. I'll do the next one over. Let's do beryllium. Beryllium is number 4. And I have no idea how many neutrons it has. It could have 3 or 4 or 5, so I don't actually care about that part. But if I drew beryllium, beryllium is this guy right here. Okay. Now, in energy level 1, beryllium has passed the first level of its video game. It hit a checkpoint. It's saved. Okay. And then beryllium is 2 out of 8 on the next one. And although I'm sure some of you would be like, yeah, keep playing the video game until you get up to 8, right? It's not actually that close to getting to the next level, to the next checkpoint, right? So what ends up happening is it kind of needs to just quit its progress. It needs to lose those 2 electrons. And what happens is these 2 electrons, we get rid of them. They're gone now. Does that make sense? But now there were 4 protons and there were 2 electrons. Is this balanced? Well, no, there's more protons than electrons now. So what ends up happening is everybody in this column gets a +2 charge because there's 2 extra of this than that. We have a name for those. We call those things cations. I've got a slide on this later, but I'll just describe it now. One of the reasons why I remember why we call them cations, this is dumb, but it works, cats have paws. They do. They have 4 paws. Cats have paws, which means cats are positive. So anything that becomes positive is called a cation. And what ends up happening is they have lost electrons. They did a little bit too much progress in the game, and they just have to like kind of lose that saved progress, and so they have to get rid of those extra electrons. I want to talk about over here now for a bit, though. Let's talk about something like fluorine. Yesterday, I would have taught you that I believe everybody in this column was -1, and everybody in this column was -2, and everybody in the last column was neutral. Do you guys remember writing that down? Let's talk about the -1 column for a bit. Let's do fluorine. Fluorine is number 9, which means it has 9 protons. Can you change the number of protons? No, because otherwise it's not fluorine. Now look at the energy level. The first energy level is 2 out of 2. It's past level 1. The second level is now 7 out of 8. Okay, you're playing your video game. You're almost at a checkpoint. Mom says, time for supper. And you're like, but Mom, I'm so close to a checkpoint. You get what I'm saying here, right? And so, okay, by the way, I'm not telling you to disobey your mom if she tells you to go for supper, but that's not how this conversation is going. But what I am saying is, would it not make sense to like take 5 more minutes, finish your level, and get to 8 out of 8? Right? In the previous example, you almost had to like drop down to like an empty level. But here what we're going to try to do is we're going to try to get to 8 out of 8. So let's say that fluorine takes an extra electron and somehow finds 1 more. That would be very stable. It's now 8 out of 8. But how many electrons does it have now? That's 10 electrons, because what is 2 plus 8? 10 electrons. Well, if you have 9 protons and 10 electrons, can you guys see how you have extra electrons now? Which is why everybody in this column is -1. And one more thought before I get back to like my written notes. Why is everybody in the last column at the charge of 0? Because it's exactly full, right? This would be the analogy of you played your video game and you finished 2 out of 2. And then as soon as you finish the video game, you hit checkpoint 1, Mom says time for supper, you're like, hey, perfect timing. Do you need to keep playing anymore? Do you need to lose any saved progress? Perfect, right? And in this one right here, not only are you 2 out of 2, but you're 8 out of 8. And here you're 2 out of 2, 8 out of 8, and 8 out of 8 again. See how everybody in the last column, they are like perfect. They don't have too few, they don't have too many. This is like the Goldilocks syndrome. You guys know like it's too hot, it's too cold, somewhere in the middle. These guys are perfect. They have exactly the right number of electrons. They don't need more or less, which is why they have no charge. So this is the last thing I need to show you guys how to do, is how to calculate an ion. So let me go through some written notes. We'll do some examples and we'll call her a lesson. Atoms have the same number of protons in their nucleus. But ions either gain or lose electrons. Either you have to get rid of some extra ones that you don't want to go back to being empty, or you have to pick up some extra ones and keep playing. Okay. Here's how you tell the difference. An atom is just written as a symbol, but an ion has a little like charge in the corner. Like for example, if I gave you Ca2+, that means it's got +2 charge. Or if I give you N3-, it means it's got a -3 charge. I need for you guys to be able to talk to me now in some examples about how many protons, neutrons, and electrons atoms and ions have. So I've got some slides here that you guys can read through. This talks about a positive ion. Cats have paws. So if it's positive, it's a cation. And here's what happened. This guy right here had 11 electrons, 11 protons, and it had 1 too many. Okay, remember how it's 2 out of 2 and 8 out of 8? It was then 1 out of 8. It had 1 extra. 2, 8, and 1 makes 11. Had 1 too many. It decided to get rid of its 1 and just be 2 and 8, which is 10. But 10 and 11 don't equal each other, right? Who wins between 10 electrons and 11 protons? 1 extra plus charge. It's called a cation. Anions work the other way. Here's an anion. Here's chlorine. Chlorine would have been 2 out of 2, 8 out of 8, and 7 out of 8. Chlorine is oh so close to being finished, right? Mom, give me 5 more minutes. Right? Well, if chlorine can find 1 more electron and bump itself up to 8 out of 8. Now it used to have 17 and 17, now it's 17 and 18. Well, now who wins? There's now one more electron than proton, so we give it a negative charge. We call those anions. So let me finish with this slide here. I'm kind of done with the knowledge part. I've talked for a long time, and I hate talking so much. So guys, thank you for paying attention this long, because this is a lot of information. Okay. Now I need to get you guys to do something. Okay. So I'm going to do a few of these, and then I'm going to give you some practice ones to try on your own. Okay. I'm going to tell you how much stuff something has, and we're going to figure out what it is, basically. So let's try an example. What if I told you that we have an element that has 17, 20, and 18? Let's start with protons. Protons defines who you are. Look on the periodic table at number 17 and tell me who number 17 is. Chlorine. Okay. So I'm now going to use the symbol for chlorine, Cl. And I knew that because of the 17 protons. And in the bottom corner goes 17. Next. 20 neutrons. The number 20 does not appear anywhere in this number. The number 37 will, though. The reason why this is 37 is that this is protons plus neutrons. Anything in the nucleus gets to go up here. And what is 17 plus 20? 37. Say that again? Can I talk about that one later? That's okay. Sorry, this is one of those ones where we got to build up to there. He's asked a really great question. If you guys look on your table, chlorine in the corner up here has the number 35.45. At a later point, if that's okay, I'd love to explain what that means and why it's a decimal number. But if it's okay for right now, can we just ignore that you ever saw that number? Okay, it's just we're not ready yet. I don't want you to bite off more than you chew, if that's okay. But I will explain it maybe later. Oh wait, last thing, we need to know how much charge this has. The charge goes on this side as -1. Now, how did I know it was -1? Well, I looked at protons, and I looked at electrons, and I noticed that there was one more electron than proton. So that's why there was a -1 charge. So this is a chlorine ion with a -1 charge. Let me try some more. Okay, this is one of those things where I got to do a couple, and then you guys got to do a couple. So the next one, 10 protons. In the same dumb analogy of the Smurfs, how do we know what to call this particular Smurf? Well, we look at its protons, and that's its identity. Its identity is number 10, so we must call this guy neon, because neon's number 10. Let me put a 10 in the corner. The next question is, how do I imply the neutrons? You will never see the number 11 in this thing here, but it'll be 21. Good job. Because these are called the nucleons. They're things in the nucleus, and that number is what we decided to put here. Lastly, I got to figure out whether I should even put a number on this side over here, because sometimes we don't even bother. And the answer is no, we're not even going to. Because can you guys see how there's 10 protons and 10 electrons? This is neutral. This is an atom, whereas this is an ion. Ions have charges, atoms don't. Yeah. Exactly. Positives are called cations. That's a positive. And negatives are called anions. Okay, now these things right here, these three are all known as something called isotopes of each other. And the word isotope basically means it's the same thing, but a slightly different variety. And the reason why they're all the same thing is that all three of these have 7 protons, which means they're all the same thing. Who's number 7? Nitrogen. So right off the bat, I'm going to do all 3 of these at once. These are all nitrogen because they're all number 7. The word we use for that is called an isotope, where they're all number 7. But they're slightly different from each other. They're not exactly the same as each other. They have subtle differences. It'd be like if you had a twin. You're more or less the same as each other, but this guy right here, I'm going to put the number 15 in the corner. That's a 15, by the way. Sorry, it didn't show up nicely. Why? Well, 7 plus 8. This guy right here, I'm going to put the number 16 in the corner. 7 plus 9. And this guy right here, also 16. That makes sense? Then for the charges, we had 7 and 7. This guy is an atom. He is neutral. This guy was 7 and 7. Also neutral. This is an atom. But this guy was 7 and 8. It needs a -1 charge, and it is an ion. Okay, a full class plus half a class later, I'm kind of done with the knowledge part of this. How'd I do? You guys kind of able to pick up some of this? Cool. You need practice though, okay? So here's what I need you guys to practice. First of all, if you would like, I will make up some examples like this. I really need to be able to go both ways. If I give you this notation, I need you to be able to go this way. Or if I tell you what this is, go that way. Does that make sense? So either I tell you what it's made of and you give me the symbol, or if I give you a symbol, I'll just do one more, I guess, one last one. If I give you an unknown symbol and I give you like a +2, a 17, and a 6, you should be able to tell me who this is. It is carbon. It has 6 protons. It has 11 neutrons. Nope, 4 electrons. It was a good try. Do you see why it wasn't 8 though, why it's 4? Because you need the protons to win over the electrons. It was a good attempt though. Okay, so let me stop my lesson here. I'm going to stop recording.